All right, today we're going to embark on a hidden quest, one that happens millions of times a second all across the globe. We're following the secret journey your phone, your laptop, any smart device really, takes to get its unique identity on the internet. We're talking IPv6 address assignment.
You know the drill. You walk into a cafe, you tap on their Wi-Fi, maybe type in a password, and bam, you're online. It just works. It feels like magic, right? But what actually just happened in those few seconds? How did your device, a complete stranger to that network, instantly get a passport to talk to the entire world? Well, it's not magic. It's a really fascinating, super fast negotiation.
And trust me, you would not want to do this by hand. Before we had all these automatic systems, you had to. Can you imagine typing in a ridiculously long address like this one every single time you went somewhere new? An IPv6 address is 128 bits long. One little typo, one wrong colon, and you're just offline. It's slow, it's frustrating, and it's so easy to mess up, which is exactly why we need these brilliant automated systems to do the heavy lifting.
So let's follow your device on this little quest. The moment it joins a new network, it's like a tourist showing up in a new city. It's anonymous, it doesn't have a street address, and it can't send or receive any mail until it gets one. So its #1 mission is to find its identity, and fast.
The grand prize on this quest is something called a Global Unicast Address, or GUA. You can just think of this as the IPv6 version of a public IP address. It's a completely unique, globally recognized address that lets your device talk to servers and other gadgets all over the planet. The key takeaway is simple. Without a GUA, your device is on a digital island, totally silent and isolated.
So how does our device get this all-important address? Well, it starts by looking for the local guide, the official greeter of the network. And in this adventure, that guide is always the router. The router has all the information, all the secrets that a new device needs to get online.
The router makes itself known by constantly sending out a special broadcast. It's called a router advertisement message, or an RA. Think of it like a town crier, standing in the middle of a square, just shouting out to any newcomers, "Welcome, welcome, here are the rules of our network and here's how you get an address to live here." That RA message has literally everything a new device needs to get started.
Now here's where it gets really interesting. The router's message doesn't just give one set of instructions. It actually lays out a few different paths a device can take to get its address. It's pretty much a choose-your-own-adventure for network configuration.
And these paths all come from two main ideas, stateless and stateful. In a stateless world, it's kind of like the Wild West. There's no central server keeping a big list of who has which address. Devices are independent. They use the router's advice to figure out their own address. But in a stateful world, it's the opposite. There's a central authority, a DHCPv6 server that's like a meticulous librarian. It manages a pool of addresses and carefully assigns one to every device that asks.
This flowchart shows how those big ideas branch out into real options. As you can see, that router advertisement can point a device down one of 3 very different paths. And the choice isn't random. It's all dictated by secret codes inside that RA message we were just talking about.
So what are these 3 paths on the menu? First, there's Slack only, which we'll just call the do-it-yourself method. Then you've got a hybrid approach, Slack with stateless DHCPv6. And last, there's the full service option, called stateful DHCPv6, where a server just handles the whole thing for you.
All right, for the rest of this explainer, we're going to follow our device down the most common and honestly the coolest path, that do-it-yourself method, which gives our devices the power to create their own identity.
The official name for this is SLAAC. It stands for Stateless Address Auto-Configuration, and the name really tells you everything. Stateless, we know that one, means no central server is keeping track of things. And auto-configuration just means the device configures itself. It does the heavy lifting to create its own address.
The whole process is really just a beautifully simple 2-step conversation. Step 1. Our device, the host, joins the network and sends out a router solicitation message. It's basically just yelling, "Hey, I'm new here. Can somebody give me the network info?" And step 2. The router hears that call and immediately responds with that router advertisement message saying, "Welcome. Here's the network info you need to get set up." And this diagram shows that little chat perfectly. You can see the PC sending out the RS message, that's the asking for directions part. And the router sends back the RA, which is basically the map for the local network. It's just a simple request and response.
And here is the end result. Success! The device takes the network info from the router, that's the first half of the address, and then it generates the second half all by itself. As you can see right here, it has created a complete, valid, and globally unique IPv6 address.
The quest is complete. Our device is officially online.
But hold on a second. How did our device know to use the SLAAC method? Why didn't it just wait around for a server to give it an address? Well, for that, we need to peek behind the curtain a little bit and learn how to decode the router's secret message.
You see, the instructions aren't written out in plain English. Instead, the router uses this simple but really powerful code that's embedded right inside that router advertisement message. And this code is made up of just 3 tiny signals, known as flags.
And here they are, the A, O, and M flags. The A flag stands for Address Auto Configuration. If it's switched on, it's telling the device, hey, you are cleared to create your own address using Slack. The O flag is for Other Configuration. If that one's on, it's saying, go ahead and create your own address, but you need to go ask a DHCP v6 server for other info, like DNS. And finally, you've got the M flag for Managed. If this flag is on, it's not a suggestion, it's a command. It says, do not create your own address, you must go get one from a stateful DHCP v6 server. This diagram shows exactly how it all works together. Check out the top path. For SLAAC only, the A flag is on, but O and M are off. That's the green light for the do-it-yourself method. In the middle, for that hybrid approach, both A and O are on. And then at the bottom, for the full-service stateful method, the M flag is on, and that overrides everything else. It's pretty amazing that this whole intricate dance is directed by just 3 simple on or off signals.
And all this brings us to a final, bigger thought. This choice between stateless and stateful isn't just a technical detail. It's kind of a reflection of 2 different philosophies for the internet itself. Are our devices autonomous individuals, able to create their own identity whenever they join a new network? Or are they more like centrally managed citizens who get their identity assigned to them by a higher authority? It's this fundamental tension between decentralization and control, playing out in a silent negotiation every single time you go online.